Okay, so yeah, welcome everyone. So I would like to wrap up my lecture with multi-messenger astronomy. And so far we have talked about cosmic rays and gamma rays, about leptonic processes of generating gamma rays. So today I would like to bring in the neutrinos, and the neutrinos are automatically connected to a multi-messenger framework. So I've tried to illustrate this with this slide here. So in multi-messenger astronomy, the subject of today's lecture, we are interested in sources like the one that is sketched here on the left-hand side. So for example, in astrophysics, you can have the situation that you have the in-spiral of a binary neutron star system. And as you might know, this in-spiral can be visible as gravitational waves, in particular very close to the merger of these two neutron stars. And the gravitational energy, which is released in this way, is then creating a very hot fireball of matter, which is driving relativistic outflows, very similar to a supernova remnant. And these relativistic outflows can be places where shocks take place, and shocks can lead to the acceleration of cosmic rays. So these cosmic rays, which are then eventually released from the source, they can also be observed. They're of course deflected by magnetic fields, depending on their rigidity, as we learned. But what could also happen is that cosmic rays in the vicinity of the source, maybe in the shock environment, or maybe after they are released from the source, they can interact with radiation and they can also interact with gas. So here's a sketch of a cosmic ray proton interacting with the nucleus. And in these collisions at very high energies, there is a possibility that you produce pions. So this is a hadronic interaction, and the pions that appear here, they can be either charged pions or they can be neutral pions. In the case of a charged pion, for example, a pi plus, this particle will have a very short lifetime. It decays into an antimuon and a muon neutrino. And the antimuon will further decay into a positron, an electron neutrino, and another muon anti-neutrinos. So the decay of the...
Nada. It wait, and it hurts.
Sorry?
I don't even want to show it.
Okay, I think that was probably per accident. Gave me quite a shock here. Yeah. So, you see that the charged pions here are a source of high energy neutrinos, 3 neutrinos, and the neutral pions, which can also be produced in these interactions, are a source of 2 gamma rays on their decay. So the interactions of cosmic rays via these 2 processes are summarized in the following 2 slides. So this is here showing the interaction cross-section of cosmic ray protons with photons. So in particular, the blue curve here, this is experimental data showing the total gamma proton cross-section. And you see here that this cross-section has a threshold. This is here 1 giga-electron volt. So the threshold is slightly above 1 giga-electron volt to account for the fact that in your interactions, you produce additional light particles, mesons, in particular the pions. So the onset of the interaction here is caused by the pion production. And you can also see that in this gamma proton collision, you start off with some broad resonances here on the left. In particular, one of these resonances, which is the production of a so-called delta plus baryon, is going to dominate the onset of this cross-section. And but then you also have later a plateau in this cross-section that is dominated by the production of multiple pions. So this is the P gamma cross-section. So this would be relevant for cosmic ray interaction with background radiation. And we also have then the interactions of cosmic ray protons with gas, which I abbreviate here in form of the proton-proton collision. Of course, if you have a proton nucleus collisions, this will scale with the number of the atomic mass number, so the total number of nucleons which are contained in the gas. And here the total cross-section again has an onset here, which is given by 2 times the proton masses, so at 2 gigaelectron-volt roughly, but it's also slightly shifted because you are producing pions. So here the total cross-section is also shown in terms of its inelastic cross-section, the part which will produce the mesons, and also the elastic cross-section, which is less dominant. So both of these cross-sections, the PP interaction as well as the P-gamma interaction, they are quite large. They have a size of about 0.1 millibar. Okay, so yeah, let me tell you a little bit more about the kinematics of these interactions. So we have collisions of cosmic ray protons, either with background radiation gamma, or we have the interaction with gas. And both of these interactions will produce secondary particles. So there can be cascades of particles, multiple hadrons that I indicate here just by a quantity x. And then we have a number of pions, which are going to be relevant for our discussion later on. So as I said, the pion, the pi plus, decays into mu plus nu mu, and the mu plus to a positron, electron neutrino, and muon antineutrino. The pi 0 goes to gamma plus gamma. And if you're looking into the decay of the pions, you will see that on average, the energy of a photon, a gamma ray that comes out here, of course, will take about 1/2 of the energy of the pion. Of course, in the center of mass system of the pion, both of the gamma rays will have exactly 1/2 of the mass of the pion. But then if you have a collision that produces pions which have some momentum, then of course the outcoming gamma rays will be separated in terms of their energy. And in the case of the charged pion decay, we typically assume that each of the neutrinos, so you have 3 neutrinos, each of these neutrinos will take about 1/4 of the energy of the pion. So in these interactions, you now need to know what is the typical energy that a pion is going to carry away. We assume that the typical pion energy on average is going to be about 1/5 of the cosmic ray proton energy. So this is a back of the envelope quantity. So that means if we are putting everything together, we can relate the emission of gamma rays and neutrinos from cosmic ray interactions to the following quantity. The neutrino energy, so each energy of the 3 neutrinos that you produce will have about 1/2 of the energy of the gamma rays, which are produced by pions from the same neutral pions from the same interaction. And this will be roughly 1/20 of the initial cosmic ray proton energy. So you can also look into collisions of heavier nuclei with gas and radiation. In that case, we would have to replace the proton here by a single nucleon of this interaction. So for example, if we were looking into collisions of iron, the energy would be the energy of the nucleon, and the nucleon energy would be about 1/A, the atomic mass number of the total cosmic ray energy. The gamma ray interaction, so the cosmic ray interactions with the gamma ray background, that is a process, as I said, that is dominated at around the threshold energy by the production of a delta plus. So a delta plus is a hadronic, is a baryon which has the same composition of the proton. It's composed out of two U quarks and one down quark. But it's appearing in an isospin doublet, a 3½ isospin doublet. So if you remember from your particle physics course, the proton and neutron, they are in an isospin 1/2 doublet, and the delta plus is part of an isospin quadruplet. So it has 4 different states, and the delta plus is basically an excitation of isospin. So this approximate symmetry in the standard model coming from the low masses of the up and down quark. So this particle, this isospin resonance, is then going to decay, and it can decay into either a proton and a pi zero, or it can decay into a neutron and a pi plus. And the relative ratio of these contribution is about 2/3 and 1/3. And this is actually coming from this approximate isospin symmetry. Quantum mechanically, you can do a Clebsch-Gordon expansion of the isospin functions of the protons and the pions, or the neutrons and the pions, and you will get this ratio 2/1 for the production of neutral and charged pion. So from that argument, you would expect that interactions with the background will produce twice as many neutral pions as charged pions. However, you have at higher energies also other resonances. You also have multi-pion production. So in general, we assume that in P gamma interaction, the ratio of charged pions over neutral pions is roughly 1, including also other channels. So for the delta plus resonance, it would be 2, but including other channels, it will be roughly 1. In the proton collisions, you, on the other hand, produce different pions of both negative and positive charge, as well as neutral pions democratically. So in that case, so you have multiple pions which you produce in this interaction, and the ratio between the charged pions compared to the neutral pions will be about 2 from the democratic assignment of the pions. So this will become important later. So the difference between these 2 quantities, when we are looking between the relation of gamma rays in neutrinos in multi-messenger astronomy. One very important example of cosmic ray interactions with radiation is interactions of cosmic rays with the CMB. So the cosmic microwave background is filling the universe, and locally at redshift 0, it has today a temperature which is of the order of 2.7 Kelvin. So this corresponds to a photon energy which is of the order of 0.7 milli-electron volt. And you can now look for the resonance process of producing a delta resonance. So you know that the 4 vector, just give me a second, I have to rearrange this a little bit. So we are looking for a 4 vector collision of the proton with the neutrino and take the square. So this will be the center of mass, energy of the collision. And this is supposed to be on resonance. So this is the mass of the delta plus. And the mass here is, mass of the delta is about 1,232 mega electron volt. So it's somewhat larger than the proton mass. And in collisions of high energy cosmic rays, and here I'm particularly interested in ultra high energy cosmic rays, you will have relativistic protons. And so you can approximate the left-hand side of this equation as the proton mass. And then if you're looking for head-on collisions of photons with cosmic rays, this would be -4 times the proton, the energy of the background photons times the proton energy. And this will give you a threshold energy of the proton. or the energy on resonance, which is given as m delta squared minus mp squared divided by 4 times the background photon energy. And this is a quantity that you can write as 4 times 10 to the power 19 electron volts for a photon background of the order of 10 milli electron volt. So this is, so 10 milli electron volt is close to the peak energy of the cosmic microwave background at about 0.7 milli electron volt. And the cosmic microwave background is actually a contribution that is dominating the cosmic backgrounds.
Sorry, there may be, it's mp squared plus 4 times, not minus, right?
It's a minus, yeah. So you basically make the following calculation. So here on the left-hand side, you have p squared plus p gamma squared. So this is the gamma. And then you have, of course, here the cross term, p gamma. So p gamma squared is, of course, the mass of the photon, which is 0. So this is a term that you can neglect. Then pp squared, this term here is going to be the proton mass. And then you have here an, so this is actually, yeah, it should be plus, not minus, right? Yeah. So this is here plus, sorry, plus. Mm. And then you're looking for head-on collision. So the scattering angle will be 180 degrees. The proton is assumed to be relativistic. So that's the reason why the free momentum of the proton is just the energy. And then you get 4 times background energy times the proton energy. Mm. Yep. Sorry. Yeah. So this was a plus sign there. Thank you. So this energy that you see here, this is a fairly high energy. This corresponds to energies of ultra high energy cosmic rays. And the way this looks is shown here on this slide. So on the right-hand side, I indicate the different cosmic ray photon backgrounds that a cosmic ray can encounter if it travels from extragalactic sources in particular. So you have here in green the very strong peak from the cosmic microwave background. Then here on the left-hand side at lower energies, you have radio backgrounds. And to the right of it, at higher energies, you have the backgrounds of infrared photons, optical photons, and ultraviolet photons. So in particular, the green and the red contribution, these are backgrounds relevant for cosmic ray propagation. And here on the left-hand side, you can see ultra-high energy cosmic ray interaction rates in these backgrounds. In particular, here the red line is indicating the collisions of cosmic ray protons with the cosmic microwave background. In these collisions, you can form electron-positron pairs via so-called beta-Heitler pair production. So the interactions of gamma plus proton that can also proceed via electromagnetic interaction. And this can produce the pairs of electrons and positrons. And the interaction rate of this beta-Heitler process is indicated here in red. So this is dominating the loss of cosmic rays in the regions between 10 to the power 10 to 10 to the power 11 giga-electron volt. But then the dashed line here, or it's a dashed gold or greenish colored line, this is the interaction rate from the hadronic interactions between cosmic rays and background photons. And you see that in particular from the cosmic ray microwave background, you get a very high interaction rate, so a very short interaction length. And this very high interaction rate will basically quench all contribution of ultra high energy cosmic rays in this energy region. You see here that the transition between the dominance of P gamma interaction and beta-Heitler pair production is at an energy of about 4 times 10 to the power 19 electron volt at this location. And so this is somewhat lower than the energy that you calculate from the peak of the cosmic microwave background. It's a broad distribution, so the interaction here are dominated by the high energy end of the cosmic microwave background, so energies that are above the peak energy of the cosmic microwave background. And this transition energy between the beta Heitler and the hadronic interaction is also known as the Gzk cutoff. So this energy here is the Gzk cutoff. And Gzk is an abbreviation, an acronym that is standing for Greisen, Zatsepin, Kutzmin. So these are three scientists who realized very early on after the discovery of the cosmic microwave background that this would severely limit the propagation of ultra high energy cosmic rays. So we will not be able to see cosmic rays at a significant level beyond this point because the interaction rate is of the order of megaparsec, and this is a typical distance between us and close by galaxies. Okay, so the last time we talked about leptonic gamma ray emission. Now I have introduced hadronic gamma rays from the production of neutral pions. We have not really talked about ways to observe these photons, so let me make a small intermission, giving you some ideas about the observation of high energy gamma ray radiation. The problem with gamma rays is that the atmosphere, the Earth atmosphere, is opaque to very high energy gamma ray radiation. So to overcome this problem, we can basically use two different techniques. So one technique is we build satellites and send them into orbit. And so we are overcoming the problem of the Earth atmosphere. And then high energy gamma rays can be detected in satellites like this here. So this is the Fermi satellite in terms of pair conversion technique. So this is here a box of the size of your refrigerator. And a high energy gamma rays is entering the satellite and produces a pair of electrons and positrons, and these pairs can be detected. And from their direction, you can infer the initial direction of the photons. So you can use this satellite to point to find the original emission of the high energy gamma rays. This type of technique works for gamma rays in the energy range from mega electron volt. Of course, the gamma ray has to have a sufficiently high energy that you can produce pairs of electrons and positrons to begin with. So between mega electron volt and tera electron volt. So this is the energy range which is covered by the Fermi satellite. If you want to go to higher energies, you again have the problem that typical fluxes of photons from the universe are dropping as you go to higher and higher energies. So you would have to build larger satellite, and this becomes not very efficient because it's very costly. Alternatively, you can do the same technique that we are using for the observation of cosmic rays. So you can have ground-based cosmic ray observatories. Unfortunately, this slide appears very fuzzy here on my screen. I'm not sure if this is the same for you. It should actually appear much clearer. Sorry for that. So you can look into interactions of gamma rays which are emitted in distant cosmic ray in distant sources. They will at very high energy interact in the atmosphere and produce electromagnetic cascades. These electromagnetic cascades have charged particles, electrons and positrons, and they are traveling faster than the speed of light in the atmosphere. That means that they are emitting Cherenkov emission, and this Cherenkov emission can be observed on ground by telescope dishes. So these are indicated here at the bottom. So this technique of observing gamma ray showers is called imaging atmospheric Cherenkov telescope. So the advantage of these imaging atmospheric Cherenkov telescopes is that you have a very good pointing resolution, a very small point spread function. On the other hand, the field of view of these telescopes is rather limited to a few degrees squared. So you really have to know where you are pointing to study individual objects in the sky. Alternatively, what you can also try is to observe charged particles which are created in the shower at the ground level. And so this technique is called water Cherenkov detection. So these are ground-based arrays that look very similar to cosmic ray observatories. And their advantage is that they have a very high duty cycle. So these observatories operate around the year at almost arbitrary weather conditions, and they have a very large field of view. On the other hand, they do not have the same angular resolution that you can achieve with imaging atmospheric Cherenkov telescopes. So the gamma ray showers in the atmosphere, they are of course in competition with many, many more cosmic ray showers that are happening at the same time. So it becomes very difficult to distinguish these showers and fish them out of the cosmic ray showers. What you can use is that the shower of a cosmic ray proton, for example, that is a hadronic cascade which will produce a lot of muon that appear in the shower at high transverse momentum. So they will produce muons that are diverting from the shower axis here in the center. Whereas for electromagnetic showers produced by gamma rays, you have a rather smooth shower core, which is dominated by electrons and positons. And in simulations, you can show that the Cherenkov emission, which is produced by these two different types of showers, look very differently on ground. So this is here the number of Cherenkov photons on ground produced by the same electromagnetic shower that I showed you earlier. So here you see that the Cherenkov cones of individual charged particles, they will add up to have this very nice Cherenkov ring on the ground, diameter of about 1/4 kilometer. And here on the right-hand side, you see the more stochastic Cherenkov emission, which is induced by these high PT muons that are produced as well. So these Cherenkov patterns show you that if you place now imaging atmospheric Cherenkov telescopes here at the center, you can nicely distinguish these electromagnetic showers from those produced by cosmic rays. But you can also look for the electromagnetic particles that reach the shower here to use the water Cherenkov technique. The state of the art in this business is shown here on this slide. Imaging atmospheric Cherenkov telescopes are placed all over the world. So we have the HESS telescope, which is located in Namibia. We have Veritas located in Arizona, the US. And we have the MAGIC telescope located in Spain on the Canary Islands. So all these observatories observe the sky in the TeV energy range. And then the state of the art of this water Cherenkov technique is the Hawk detector. So this is a detector which is located in a mountain range in Mexico at high altitude. So HAWK stands for high altitude water Cherenkov detector. And you see that these water Cherenkov detectors, which are placed inside these tanks, are standing very close to each other. This is to have a very good coverage of the electromagnetic shower core, which is produced above the detector, and to distinguish this from hadronic showers. And here is one very beautiful example of gamma ray observation taken from the Fermi satellite. So the Fermi satellite orbiting the Earth has the big advantage that you can point it in any direction, and you can make a survey of the gamma ray sky in arbitrary directions. So this is here showing you the gamma ray emission in galactic coordinates. You clearly see a very broad emission here coming from the galactic plane. but you also see hotspots above and below the galactic plane. These are all indicating high energy gamma ray sources of extragalactic origin. Most of these bright spots that you see here are actually active galaxies that have a jetted outflow, which is pointing into our direction. These active galaxies are called blazars, and they appear as very bright gamma ray sources in the sky. So if you look here at the bright emission from the galactic plane, you can identify again various components of the gamma ray emission on a statistical basis. Of course, for each photon, you don't know if it's produced by leptonic or hadronic interaction, but you can do a template fit to the emission from the galaxy. And here I show you two examples. This is here the emission observed with Fermi from the galactic center region on the left, and on the right-hand side, you see the diffuse emission of the galactic plane above and below the galactic plane. And we can identify here various components, also components that we talked about last time. In green, you see inverse Compton. So this is produced by high energy electrons, which are scattering with background photons, in particular the cosmic microwave background. So this is a significant component. And also Bremsstrahlung emission of high energy electrons with gas is indicated here in cyan. And these two components are important for the template fit. But in both of these cases, the dominant contribution is actually coming from cosmic ray propagation in the galaxy and interaction with gas. And this produces hadronic emission in form of pi0 decay. And this is indicated here on both sides as the red line. So this is indeed another indication, another proof that cosmic rays are propagating through our galaxy. And it's another way to also measure the relative density of cosmic rays in different places of our galaxy to look for the relative gamma ray contribution. Another way to have a proof of cosmic ray acceleration in supernova remnant is shown on this plot here. These are again observations with the Fermi satellite of two old supernova remnants, IC443 and W44. So these are old supernova remnants. The very energetic cosmic rays have long left these sources, so they are dominated at the lower energy of the spectrum in the GeV energy range, which is peaking in the observing band of the Fermi satellite. And what you can observe here, together with the data points in red and blue, are model fits to the emission. And here you see a model in dashed lines, which is based on Bremsstrahlung of high energy electrons in these sources, compared to the production of hadronic gamma rays via pi0 decay. And you can see that in the case of the pi0 decay, you manage to produce this very sharp drop of the emission below about 200 mega electron volt for both of these sources. And so this is actually expected for hadronic gamma ray emission because of the threshold effect. You need to produce the pion, the neutral pion, to begin with. And in the rest frame of the pion, the gamma rays will have an energy of about 70 mega electron volt. And then in the boosted framework of cosmic ray protons, which have an energy of the order of giga electron volt, this threshold in the rest frame of the pion translates into a break in the spectrum that is about at 200 mega electron volt. This is the so-called Pion Bump. And by observing this Pion Bump, we have another smoking gun of cosmic ray interaction in the sources and the dominance of hadronic emission from these sources. Are there any questions at this point?
I have one question. Could you go back to page 6?
6. Mm-hmm. Yeah.
Yeah, for the left plot, I don't quite understand. I mean, look for the red solid line. It's
Yeah.
interaction rate, right? It means for the even higher energy of the proton, the interaction rate start to become more and more small, right? That's
Yeah,
mean for the even higher, for example, 10 to 12 GeV.
Yeah.
It can reach to Earth, right? I'm not sure.
Yes, so sorry, this might not have been entirely clear. So what I'm trying to show here is the individual interaction rates of sub-processes. So the red line is showing you the electromagnetic interactions of cosmic ray protons with background photons, in particular the cosmic microwave background. Mm-hmm. And this process can produce electron-positron pairs. This process is called beta Heitler. And you see that in this process, the interaction rate is indeed going down again as you go to higher energies. But at the same time, you also have the competing process of cosmic ray interaction via hadronic processes. And this will lead to the production of pions. So both of these processes happen at the same time. And while the beta Heitler process is turning off in terms of its rate, the hadronic interaction takes over and it has a much, much higher rate. So you basically have to take the sum of these two contributions together to get the total interaction rate.
Okay.
Yeah, sorry, this was not entirely clear. So you see this line here reaches here a value of the order of 0.1. So this is inverse megaparsec. That means here you reach an interaction length of the order of 100 megaparsec. It means that cosmic rays will only manage to travel 100 megaparsec towards us before they get absorbed by this process. And 100 megaparsec, that is also the typical distance in the universe between local galaxies. And so if you have an extragalactic source which is sitting in another galaxy, then it is very difficult that if the source produces very energetic cosmic rays around 10 to the power 12 gigaelectron volt, that these are actually going to arrive at Earth. Okay. And so in the spectrum, you would expect to see a sharp drop, which is actually also observed at this energy of the Gzk cutoff.
Okay. Okay. For the to make sure for the yellow dot line, it means the gamma plus proton to proton pion, right? For this process, right?
Yeah, exactly. So this would be so this line here. Let me maybe indicate this here. So this line here would be the E plus E minus production, and this line would be the pi plus minus pi zero production.
Okay.
Yeah.
Thanks. It's more clear now. Okay.
Yeah, I'm sorry. I was maybe a bit rushing over these slides. Okay. Yeah, so I mentioned there are ways to get strong evidence that cosmic rays are accelerating in the source by doing these template fits and spectral fits to the data. However, a more convincing way to convince ourselves that we have actually cosmic ray sources is by the detection of the neutrinos. So the neutrinos from the charged pion decay, they will of course also be emitted by the same type of process. And since they are neutral particles, they will not be deflected along their propagation towards Earth. So we do not have to worry about absorption processes. For example, for the gamma rays, they can interact with the cosmic microwave background and produce cascades, or cosmic rays which are deflected in magnetic fields. Neutrinos will just go on a straight line and arrive at Earth. So this makes neutrinos actually probably the most ideal cosmic messengers. So they directly point back to the sources. They arrive at the same time as gravitational waves and photons. So they are also ideal for real-time multi-messenger astronomy. And they are smoking guns for the presence of cosmic ray sources, because there's no other process at very high energies that can give you a flux of high energy neutrinos. But on the other hand, the detection of these neutrinos is very challenging. And this is the great challenge we have to face when we are talking about neutrino astronomy. Again, I apologize that this slide appears very fuzzy on your screen. I don't know what the reason is. It appears fine on my tablet here. But maybe you can read what I was trying to write here. The neutrino interactions at low energy, they are happening in form of coherent interaction, quasi-elastic and resonant interactions with nuclei. At high energies, and here I'm talking about neutrinos of the order of, with energies of the order of tera electron volt or peta electron volt, they will interact with nuclei via deep inelastic scattering. So here on the left-hand side, you see a sketch of a scattering process of a high energy neutrino with a with a nucleus. So this would be matter at rest. And the interaction in deep inelastic scattering is happening with individual constituents of the nucleon, so-called partons. So these are individual quarks. And the neutrino is a weakly interacting particle. That means it can exchange W bosons or Z bosons with quarks in the nucleon. And if you exchange a W boson, which is a charged particle, you also talk about charge current interactions. And in the exchange of the Z boson, a neutral particle, you talk about neutral current interactions. So these processes are weak processes. And if you calculate the total cross-section, you arrive at something which is indicated here on the right-hand side, but I see that you will not be able to read off what is written here. So maybe you have to look, you can have a look later on in my slides. So the interaction cross-section is very low. For example, here for charge current interactions, so exchange of a W boson, at an energy of 1 peta electron volt, the interaction cross-section is of the order of 1 nanobar. So this is about 8 orders of magnitude lower than the interaction cross-section of protons with protons. So that's a blessing for neutrino astronomy. These neutrinos are not getting absorbed by any gas, but it's very challenging if you want to detect these particles. And you can make a very quick back of the envelope calculation. So for neutrinos, as we will discuss later, there's a typical flux level for high energy neutrinos. And this flux level F nu is of the order of 1 neutrino per 10 years and 1 square meter. So this is for neutrinos at an energy of about peta electron volt. And this flux level, as we will learn later, this is also called the Waxman Barcal upper limit. And it's very close to observations that we have recently done with the IceCube observatory. Now, as I said, the cross-section in deep inelastic scattering for neutrino energies of the order of peta electron volt, they are at the level of about 10 to the power minus 8 of proton-proton interaction. And this means that the rate is at the level of about 10 to the power minus 9 barn, so 1 nanobarn. And this is equivalent to 10 to the power minus 33 centimeter squared. So this is a very low quantity. Now, if you want to detect neutrinos, you can now make the following simple calculation. So the number of events that you want to observe, the event rate, should be sufficiently large. And the event rate of collision that is going to be equal to the cross-section in deep inelastic scattering times the flux of the neutrinos. And then you have to assume that you have a detector with sufficiently many nucleons for to increase the chance, the probability that your neutrino is actually interacting. So typically in matter, you have about Avogadro number. So Avogadro number is 6 times 10 to the power 23. So Avogadro number atoms per cubic centimeter. So, and you want that you have an event rate which should be sufficiently high that you at least see 1 neutrino per year, let's say. I mean, this is a very low rate, but so in this way, you over a couple of years, you will collect enough neutrinos that you can actually do neutrino astronomy with these events. So, and it will turn out that if you do this calculation to see of the order of 1 event per year with this given flux, you need a detector volume that is that has a size of about 1 cubic kilometer. So from this simple back of the envelope calculation, you see that it's completely unfeasible to build a neutrino detector the same way as we build other telescopes. So you cannot simply build something that has a volume of 1 cubic kilometer. I hope you realize this. So the only way to detect neutrinos is actually to find natural resources of material that we can utilize for neutrino detection. And one way to look for these neutrinos is to go to transparent media. So in transparent media, for example, ice or water, and maybe other methods, you can then look for secondary particles which are produced by the interaction of neutrinos. And these secondary particles will appear at high energies. And similar to the atmospheric Cherenkov emission, these high particles, if they have high energy particles, if they have a charge, will emit Cherenkov emission. And this, in fact, is the way that we successfully detect neutrinos these days. So the state-of-the-art detector for high-energy neutrino detection is the ice cube detector. This is a detector that is located at the South Pole. At the South Pole, you have a glacier that has a thickness of about 3 kilometers. So this is snow that has fallen over thousands of years and is compressed to form very clear ice. And you can utilize this very clear glacial ice for the process that I just talked about. You have a high energy neutrino, which is interacting in the vicinity of the detector. And if you have a charge current interaction, this high energy neutrino can produce a high energy muon. And as this muon is traversing the detector, it will emit Cherenkov light. This is indicated here as this bluish cone. So the only thing that you have to do now is you have to drill holes in the ice. And this is what we've done for IceCube. We've drilled holes, or rather we melted holes into the ice. And then we placed optical modules. So these modules are based on photomultiplier tubes, very sensitive detectors of individual photons. And with these photomultiplier tubes, we can now wait and try to see if we have a high energy muon which is passing the detector. And if this happens, then it could be a candidate of a high energy muon neutrino which is interacting, producing this type of event. Are there any questions?
Yes, I wanted to ask if the transparency is required to catch the Cherenkov light emitted by the muon interaction.
Yes, so the emission, you probably know these images of nuclear reactors, so man-made nuclear reactors which are placed in water. You see this bluish glow around the reactor, which is produced by high energy electrons produced by radioactivity. And the same effect is also visible for, so the emission of this strength of emission will be visible to your own eye if you have sensitive enough eyes. Yeah. So if a muon is passing through the eyes, then it will emit a bluish glow, which can be observed in the PMTs. Of course, the ice has to have the property that it does not have a strong absorption of this emission. And actually, for IceCube, no one really knew what the optical properties of the glacier is at the South Pole. So this was a bit of a bet that you had to make. But the absorption lengths of photons in the ice are of the order of a couple of 100 meters. So this allows actually to observe these photons if you place your optical modules at the distance of about 100 meters. In fact, so the cubic kilometer of optical sensors. So these are arranged along these readout cables, which we call strings. And the distance between these strings is about 125 meters. So we were lucky in the end. Okay,
this geometry allows to determine the arrival direction of the particle, of the neutrino.
If you give me a second, I will show you some examples actually. Yeah, so let me progress. So before I show you examples, let me briefly tell you about another challenge that we have to face in neutrino astronomy, and that is backgrounds. So cosmic rays which are interacting in the atmosphere, as you know, produce showers. And these showers also contain neutrinos, and they contain muons. And these muons at the South Pole, they can penetrate the surface and shower all the way down into the detector. So there's a constant flux of cosmic ray muons, which is crossing the detector at the South Pole. And also the neutrinos, which are produced in interactions in the atmosphere, they can be observed in the detector. And of course, you want to look for neutrinos which are produced in astrophysical sources. So these neutrinos are a background of neutrino detection from astrophysical sources. So one way to overcome this is the following. So this is a sketch here of the IceCube detector at the South Pole. Given this number that I gave you of about 1 event per 10 years and square meter, this same flux will give you about 1 event per year at 100 tera-electron volt at somewhat lower energies. So a cosmic neutrino, because it's weakly interacting, it can actually cross large parts of the Earth. And then it can interact in the vicinity of the detector. And if the neutrino has the right flavor, in this case, a muon neutrino, and if it undergoes a charged current interaction, it will produce a high energy muon, which is then producing this Cherenkov glow in the detector. So this would be the type of signal that we are looking for. But on the other hand, we have these cosmic ray interactions above the detector, producing muons. And on top of 10 astrophysical neutrinos per year, we have about 60 billion atmospheric muons every year. I say we here because I'm actually a member of this collaboration. Yeah, so it's kind of personal for me. And then, as I said, these cosmic ray interactions produce atmospheric neutrinos. And so you could also imagine a cosmic ray interaction on the other side of the Earth. You won't see the muons from this event, but you see the atmospheric neutrino that is interacting again close to the detector and produces a muon. So one way to get rid of these large background of cosmic ray muons is to simply select those events which are upgoing in your detector. So not downgoing events, which are most likely produced by cosmic rays, only upgoing events. And then you only have to battle here between atmospheric neutrinos by cosmic ray interaction and astrophysical neutrinos. but there are ways to look for the spectrum of these particles to win this battle. Another way to look for high energy neutrinos is a so-called Veto Technique. So here's another sketch of the ice cube detector here viewed from the side, and these little dots here are optical modules attached to strings. And if you have a large detector, you can define the outer layer of optical modules as a virtual veto region. And now you are only selecting those events that are happening inside your detector without any strength of light detection in your veto layer. And this is another way to detect neutrinos for the following reason. If you, for example, have a cosmic ray interaction above your detector that is producing atmospheric neutrinos, then the same shower at the same time will also produce many muons, which are triggering this veto. So this veto technique is a way to get rid of atmospheric backgrounds, because these atmospheric backgrounds are automatically triggering the veto layer. And so in your analysis of the data, you can deselect these events. On the other hand, if you have a cosmic neutrino, which is coming from the other side of the Earth or from above the detector, that can start inside the detector and produce an event. This alternative event selection is called a high energy starting event selection. And this was actually the selection that led to the discovery of high energy neutrinos with IceCube. And here is now, Michele, two examples of how this would look like in your detector. So here on the left-hand side, you see in these colored dots the amount of Cherenkov light that individual modules were observing. And the color here is indicating at what time relative to the event the Cherenkov photons arrived in these modules. So red means early and blue means late. So in this type of event, what's happening is the following. You have a high energy muon neutrino, which is coming here from the left and produce a collision inside the detector. So at that point, it has passed the veto layer. So it's fine. It's going to be selected. And this first event will lead to a cascade from the breakup of the nucleus. And this Cherenkov emission from charged particle of this cascade will have a spherical emission here at the beginning. But then in this muon-neutrino interaction, you produce a high energy muon, which is then going to the right and leaving the detector to the right. So you can imagine that for these type of events, we have a relatively good pointing accuracy. So we simply have to find the direction of this outgoing muon. And we know then that the initial neutrino was coming from this direction. So this is the way neutrino astronomy works, looking for these high energy muons. What can also happen in this high energy starting event selection is that you only produce cascades. So this will be an interaction of any type of neutrino via a neutral current interaction. This will not produce any high energy secondary leptons, charged leptons, which exit the detector and can identify the direction. Here you only see this spherical cascade emission from secondary charged particles from the breakup of the nucleus. So these events are also called cascade event because of the spherical nature. These events are very interesting because they allow you to measure the neutrino energy with very high accuracy. This event, for example, is an event with an energy of the order of 1 peta-electron volt. So this is one of the most energetic neutrinos that was ever observed. And this type of neutrino clearly has an astrophysical background because we will not expect that atmospheric neutrino interaction produce many of these high energy neutrinos. Unfortunately, due to the topology of this event, it's very difficult to identify the original direction of the neutrino. So this is a problem of these type of events. So by now we have collected many of these high energy events with IceCube, and this is here showing you a comparison of the neutrino flux that we observe. And so here, this on the horizontal axis, you see the log of the energy. On the vertical axis, you have the flux of the neutrino times energy squared. So this is a measure for the density of the energy density of the emission. And here in the middle, you see the neutrino emission that is dominated in the energy range between about 100, 10 to 100 tera electron volt up to a few peta electron volt. So these cascades that I just showed you are sitting here and are part of the emission at the upper end of this neutrino spectrum. What's interesting here is if we compare this to the observed isotropic emission of gamma rays from the cosmos. So this is done again with the Fermi satellite that I talked about earlier. You can see that the flux level, or the energy, the intensity of the gamma ray flux is comparable to that of the neutrinos. And also, if you look here to the right, you have flux of ultra high energy cosmic rays, which are observed by these Auger observatory that I introduced on Monday. So this one of the state-of-the-art instruments to observe ultra high energy cosmic rays. They also have an energy density above the Gzk cutoff, which is here, that is comparable to the intensity. So there might be very interesting multi-messenger connection between gamma rays and neutrinos, and also neutrinos and ultra high energy cosmic rays. But before I talk about these multi-messenger relations, let me tell you a little bit more about the neutrino emission here. So what we observe in neutrinos are energies of the order of peta electron volt. And so, as I said earlier, neutrino, gamma ray, and cosmic ray nucleon energy is related via this relation in hadronic interaction. So for every PeV neutrino that we observe, we require a cosmic ray particle that has an energy of the order of 20 peta electron volt per nucleon. So if we have cosmic ray protons, this would correspond to the vertical green dashed line here. If we, on the other hand, have cosmic ray iron, then we have an energy that is 56 times larger because of the atomic mass number of iron. That would mean that the cosmic ray would have an energy which is just above 1 exa electron volt, 10 to the power 18 electron volt. What's interesting, and this is what I want to point out, the energy range that I discussed from proton to iron is basically part of this cosmic ray spectrum, which is above the knee and below the ankle. We talked that the cosmic ray below the knee are most likely produced by supernova remnants in our galaxy. We know that cosmic rays that appear above the ankle, they are actually produced by extragalactic sources. But we don't really know what sort of population dominates in this intermediate region between knee and ankle. So it could be a galactic contribution that is very energetic, or it could be an extragalactic contribution that dominates here. So just from the energetics of the source, we don't really know. For neutrinos, we also have another degree of freedom compared to photons, which is the flavor of neutrinos. So neutrino flavors, neutrinos are produced in 3 different flavors: the electron, the muon, and tau neutrino. And the definition of electron, muon, and tau neutrino is basically that in charge current interaction by the exchange of a W, these neutrinos couple to an electron, a muon, and a tau lepton. This is the definition of these flavor states. Now, if you have neutrino production, say by collision of cosmic rays producing pions, then from the decay of the pion, you would expect to see 1 electron neutrino compared to 2 mu neutrinos and 0 tau neutrinos. So this is the initial flavor on production. And here I'm not going to distinguish between neutrinos and antineutrinos. That is not so important for the observation in IceCube. So pion decay would give me 2 mu neutrinos, 1 electron neutrinos, and no tau neutrinos initially. But now you might know that neutrinos are also oscillating, because the flavor states that I indicate here, they have a superposition with different mass eigenstates, and these mass eigenstates have different masses. So once a neutrino mix is produced by the source, and here on the left-hand side you see a ternary graph. Every point in this ternary graph is giving you the relative contribution of electron, muon, and tau neutrinos. And so the 1 to 2 to 0 composition here is sitting at this location initially, but then in time, due to vacuum oscillation, after release from the source, you will have an oscillation pattern. So neutrinos will start to oscillate. However, this oscillation is not going to be visible in a neutrino detector that is very far away. And the reason for that is the neutrinos are typically emitted following a spectrum, so they have not a fixed energy. And also your detector is not going to resolve individual energies of neutrinos very well. Typically in IceCube, we have an energy resolution of the order of 10%. So these oscillations will be averaged out once the neutrinos arrives at the detector. And so this oscillation pattern will basically reduce then to the flavor composition that corresponds to the oscillation averaged flavor mix. So the 1 to 2 to 0 contribution will give you an observed flavor composition, which is at this very central point in this flavor diagram, this ternary graph. And that means that it is likely to have either type of neutrinos, electron, muon, and tau neutrinos. They should come all at the same probability at your detector, if initially these neutrinos are produced by pion decay. You can also think about the production of, let's say, electron neutrinos. So this happens if you have the decay of a neutron into a proton and electron and an electron antineutrino. If this was the dominant source of neutrino production, you would start at this point in your diagram. But then also here you will start an oscillation pattern, which will average out. And the average contribution would then end up here at this location in this diagram. So it will not be a 1-to-1-to-1 contribution as in the case of the pion, but you will always have a significant contribution of all neutrino flavors after you take into account the oscillation. I believe next week you will also have a dedicated lecture on sterile neutrinos, and I think this the neutrino oscillation phenomenon will be discussed at that point at great length, so I'm not going to talk more about this right now. But if you have any questions right now, I'm happy to answer this. Okay, then let me continue. Yeah, so this is then the observed neutrino flavor mix. Here again, you see different possible initial condition as the circles. And these colored plots here in this diagram are the observed oscillation averaged flavor compositions. And what you see here in the background in black is a likelihood contour from IceCube, and you see that the observation of this detector is consistent with the production of pions in astrophysical sources. So this is another confirmation that what we see in IceCube at very high energies is actually produced by cosmic ray interactions. Now, what is the origin of this emission? The bottom line is we don't know. So we see a very significant emission in the universe of high energy neutrinos, as I indicated by this flux diagram, but we don't really know what type of source is producing this emission. What you see here on this slide is a summary of very energetic events that we see in IceCube. And these magenta contours here are indicating our angular resolution for our cascade events. So you see that we have some resolution, but it's a very poor resolution. In some cases, we have an angular uncertainty of the order of 10 degrees. So this is very poor for astronomy. But if we observe these high energy tracks in the detector, for example, in the form of upgoing muons, then the location is much better. It can be of the order of a fraction of a degree. So what you see here in the slide is events observed with this high energy starting event technique in magenta. They are dominating the southern sky. So from the point of view of IceCube located at the South Pole. This is here in turn a map showing you galactic coordinates. So the Earth horizon is shown here in this plot as the dashed black line. So we have, of course, the Earth axis is tilted as we are moving around the sun, and the projection of the equator onto the galactic plane is indicated here by the black dashed line. So you see these high energy starting events here in the southern sky, and the red dots here are indicating high energy events observed with this traditional technique where you're just looking for upgoing events and compare the energy to the atmospheric neutrino background. So this is the traditional way of observing neutrinos. These events are not isotropically distributed across the sky map, but the structure that you see here in the sky map, that is mostly dominated by either Earth absorption. So some neutrinos at very high energies will also get absorbed in the Earth, or by the event selection technique in the data analysis. So if you do the statistical analysis, taking into account also the selection effects of these events, we cannot observe any strong correlation of these events with known astrophysical sources, except maybe for some candidates that I'm going to talk about later. So the situation that we are facing in neutrino astronomy is maybe comparable to very early gamma ray astronomy. So this is one of the first sky maps that was produced for gamma ray astronomy in the 60s based on gamma rays that were observed with a satellite called the Orbiting Solar Observatory. And in these very early gamma ray maps, you could already identify some excess of gamma rays close to the galactic plane. Maybe if you squint your eyes, you can see this. It smears out here in the galactic center and galactic plane. But of course, at this point, you could not identify any extragalactic sources. But 50 years later, we have observations with Fermi, and I've already showed you this the sky map before. And now with better techniques, with more data, we clearly see now many different structures, in particular from our own galaxy. And hopefully neutrino astronomy will also eventually, maybe after 50 years, when we are all old, where you can identify individual neutrino sources the same way as we see it now in this Fermi sky map. So how can we, so are there other questions at the moment? Maybe I should break for a little. Okay. So I mentioned we observed a very high energy diffuse flux, but we haven't observed strong neutrino point sources. How do these two observations fit together? If you have a strong flux of sources, and if this flux of sources is dominated by extragalactic sources, then I would also expect that there is a chance that I can identify individual sources, in particular close by sources, as very bright individual neutrino sources, and my detector should pick up on them when I analyze my data. So to understand this observation, I wanted to walk you through a comparison between the diffuse and the individual point source fluxes from extragalactic source population. So in the following, I'm going to assume an extragalactic population of sources. And I will assume in the following that individual sources emit neutrinos following a spectrum which I call Q, nu, E. So this is a source term of neutrinos following some spectrum. It could be maybe a power law spectrum. It could also be something else. So in the following, I assume that all the sources are equally emitting neutrinos, so there's no individual difference between source and source. These sources are also called standard candles. So if we now look for the observable flux, of a source that is at redshift Z. So in cosmology, so I don't have the time to give a revision of cosmology, but redshift in cosmology is of course our way to measure large distances. So redshift Z means that we have a source in our population which is sitting at a certain distance from Earth. So the observed flux is given for the neutrino source as follows. So F here is my flux of the source which is sitting at redshift Z, emitting the energy E. And this flux for cosmologically distant sources is given as 1 plus redshift squared divided by 4 pi dl squared, and dl depends on redshift Z. So dl here is a quantity in cosmology which is called the luminosity distance. And in standard cosmology, which is dominated by dark energy today and cold dark matter, so a flat universe, this quantity is related to the Hubble expansion of the universe. And it's given by this integral here, the integral between 0 and redshift Z. And then you have dz prime 1 over h z prime. And this is here the Hubble parameter at redshift Z, which is given by the Hubble parameter observed today. And then this scales with the dark energy fraction of the energy density of the universe, and the matter fraction today, and the matter fraction has the scaling that goes like 1 plus redshift to the power 3. And in standard cosmology, this quantity is about 70%, 0.7, and this one is about 30%. So matter, in particular cold dark matter and dark energy, are dominating the expansion of the universe today at redshift 0. So this is the definition of the luminosity distance. And we are not done here with the flux equation. So this is the scaling of the source flux, Q nu, at the energy E. But now the energy has to be multiplied by the redshift factor, 1 plus Z. So that means if we observe the energy of a neutrino of the order of E coming from a source at redshift Z, then the source has to emit this particle at a somewhat higher energy, which is given by the redshift factor 1 plus Z. So this is the emission of an individual source. And the luminosity distance here is actually defined by in the following way. So you can do this as a consistency check. So the total energy fluence, which is defined as the energy integral times the energy times the flux of the source, that should be given as the total luminosity of the source divided by 4 pi dl squared. So this is actually the definition of the luminosity distance. If you have a known luminosity of a source at redshift z, and you observe this energy flux, then this allows us to measure the luminosity distance of the source. And this is a way to do cosmology. Now, if you plug in the numbers, so the definition here of the point source flux on the left-hand side, you can show that this is identical to the expression here on the left-hand side, because the luminosity for us, luminosity is simply given as the energy dE E times the emission Q nu E. So you can show that this is actually an identity. And this also explains why we have to introduce this additional factor 1 plus z squared to this equation because of this energy integral dE. Any questions on this calculation? Okay, so this is the emission of a source with a given spectrum. Now, on the other side, on the other hand, we can also look for the total emission of all these standard candle sources in the universe. And the total emission follows also a very simple quantity. So the total isotropic emission from the population is the following. So for the isotropic emission coming from all direction of my extragalactic population, that is given by this quantity J nu. And this diffuse flux, this isotropic flux, is given as 1 over 4 pi to average over the direction across the sky. And then I simply have to integrate over redshift. And I multiply, I account for the contribution of individual sources. So this is the flux that we have introduced earlier. But now we also have to introduce the number of sources. And the number of sources is taken into account by a so-called co-moving source density. So this factor rho is going to be the co-moving number density of the sources. And then we have to find a relation between the co-moving volume and the redshift z. So we have to multiply this here by the integral of the co-moving volume divided by redshift. So this will be a calculation of the isotropic flux. Now the co-moving volume is defined as 4 pi over 3 times the co-moving distance to the power cube, to the power 3. And in standard cosmology, the co-moving distance is related to the luminosity distance by dividing a factor 1 plus z. So this is for a flat cosmology. Now this derivative d vc over dz can now be performed. So here you have to use the definition of the luminosity distance. If you divide this by this factor 1 plus z, this factor drops out. So you only have this integral. So this volume derivative will simply give you 4 pi co-moving distance at redshift z squared divided by the Hubble constant at redshift z. So if you put this here into this equation And if you also include the expression of the individual point flux that I have given you on the right-hand side, you will find that the total emission, J nu E, can simply be written as 1 over 4 pi dc, so redshift integral, and then you have rho z over hc times the flux of individual sources at energy E, but here again you have to multiply it by this redshift factor to account for the redshifting or the blue shifting of your observed energy towards the source. So this is now the isotropic diffuse flux. And this is yeah.
In the first formula, the F nu. No, next page. Yes,
this formula.
Yeah. In the first formula, it's Z1 or.
No, sorry. This is a comma. So this is a quantity. This is the same as here. So I have a function that depends on energy and redshift.
Oh, that's a comma. Okay.
This is a comma. Yeah. So this is not Z1 times E. This is Z comma E. So this is so you can take Z as a parameter. It's a spectrum for a source at a distant Z. Yeah.
Okay.
So, and you see you have here 1 plus Z squared over dl squared. This is basically 1 over co-moving distance squared. And this will exactly cancel this factor 4 pi co-moving distance squared.
Yeah. Yes.
Such that the final equation looks like this here, right?
Yes.
So, so this is the diffuse flux. This is what IceCube observes with high significance. And you can write this diffuse flux, so this expression in the following way. So you can massage it a little bit. You can write it as 1 over 4 pi. And then you basically extract here the density at redshift 0. So this is now an index, rho 0. So the local density of sources divided by the local Hubble constant. And if you integrate here over the energy of the neutrino, you basically get this fluence, the neutrino fluence, the energy fluence. And this will then depend simply on the luminosity of the source. So you combine the energy integral here with the emission spectrum. And then you can combine everything else into the following integral. So this is the integral over dz. And then you have here rho z over rho 0, h0 over hz. And then you have another factor 1 over 1 plus z squared, which comes in due to the energy integral that you have here. This quantity here on the right-hand side, this is a dimensionless. So once you do the integral, it's a dimensionless constant, which is in the following called psi or zeta z. So this is a factor that accounts for the expansion of the universe. So for example, and this is something that depends on the redshift evolution of the sources. If you have, for example, bring this up. So if you have a constant co-moving volume, then these zeta z factors will be about 0.5. So this would be a universe where this evolution of sources is constant. So this is just the local density. But if you have, for example, a more realistic redshift evolution of sources, for example, sources that follow the star formation rate in the universe, then this will be something that is closer to 2.6. So this would be for the star formation rate evolution of sources. So the bottom line is all these factors are typically of order 1 and give you a small correction to this balance equation. So in the end, we can now write the fluence of the neutrinos, which is observed by IceCube, as 1/4 pi rho 0 times L nu divided by the local Hubble expansion H0 times this redshift factor u, which is an order 1 factor. So you see that this quantity is proportional to the local density of sources and the luminosity of sources. And this combination, the product, is fixed by the observation with IceCube. Fixed by IceCube. So on the other hand, what you can also show, and unfortunately I will not have the time to go through this in great detail, you can also show that the population of sources that we were talking about. So in this picture, so you have now we have calculated the total emission coming from all of these distant sources that we observe locally. But now we will also would like to make an estimate what the contribution of the closest sources in our universe is. And compare this to the sensitivity of IceCube to observe individual sources. And I will not give you the detail now of this calculation. You can maybe look this up in the references that I gave you. You can estimate that the fluence of one individual source, so this is the closest source, will be given as a quantity that goes like, again, the luminosity of the sources, and then the local density to the power 2/3 divided by 6 to the power 2/3 pi to the power 1/3. So you see this is proportional to neutrino luminosity of the sources times local density to the power 2/3. And from the fact that we in IceCube or other observatories have not found very strong neutrino sources, requires that the contribution of the closest source should be smaller than our detection threshold. So our 5 sigma detection threshold of individual sources. And for IceCube, this is at the moment something at the level of 10 to the power minus 12 tera electron volt over centimeter squared and second. Yeah, so unfortunately, I do not have the time to derive this expression with you, but it's a very elementary calculation. So putting these two pieces together allows us then to make a comparison, and this is shown here on this slide. So the magenta line, maybe if we focus here for a moment on the left-hand side of this plot, the magenta line here, this is basically showing you our isotropic flux. And as I said, the isotropic flux fixes the combination of the local density rho and the neutrino luminosity. So the product of these two quantities is fixed, and you have some variance coming from the statistical uncertainty of the observation, as well as from the different evolution models of the sources. This is the reason why you have a wide band here. Any source which is located in this vicinity, so any population of sources, would be sufficient to explain the neutrino emission that we observe at PeV energies. On the other hand, the second calculation of the local contribution of the closest source, that was scaling as the luminosity times the density to the power 2/3. And this has to be smaller than our detection threshold. So this is introducing another line here, which is now somewhat tilted because of the different dependence on the effective density. And so the blue shaded region here is the part of the parameter space which is effectively excluded. simply coming from the fact that we have not observed high energy neutrino sources. And you can see that there are actually source populations in the universe which are very rare. So rare means that you are walking down here the effective density of the sources. But on the other hand, they are also very energetic. They have a high luminosity, in particular blazars. So these are these active galaxies with a jet pointing in our direction. So they are observed with a very high luminosity. And unfortunately, these sources that dominate the gamma ray sky are actually not good candidates for the isotopic flux. On the other hand, if you walk down to the left of this figure, we have other candidates like starburst galaxies, which are galaxies that are like our Milky Way, but they undergo a period of high star formation. And this also makes them good sources of cosmic ray production and neutrino emission. So these sources are more abundant, but individually they have a very weak luminosity. And so for that reason, they are at the left-hand side of this plot. These sources are still consistent with the non-observation in IceCube, which is indicated by the blue region here. So starburst galaxies in particular are very good candidate sources of the isotopic emission that we see. You can also do the same kind of exercise with transient sources. So here you parameterize your space in terms of the total energy emitted from the source and the local rate density. So how many sources appear in a certain time, in a certain volume. And you can do a very similar estimate here. Again, the diffuse flux is fixed by the product of these two quantities, and the non-observation allows us to exclude rare sources, but luminous sources like, for example, gamma ray burst events. Are there any questions on this comparison? Okay, so the bottom line of this discussion is it is consistent that we have observed a high intensity flux of extragalactic neutrino sources without observing individual neutrino sources if the underlying population is dominated by sources that appear very frequently in the universe and are not strong individual emitters of the neutrino emission. Now, in the last, I don't know, 10 minutes or so that I have left for this last lecture, I would like to talk about multi-messenger relations. So, as I said, the neutrino production that we observe in IceCube is also related to the simultaneous production of pi zeros. And you can make a simple balance equation between how many neutrinos should appear together with photons. And so if we again introduce a term, an emission term that I call here for the neutrinos Q nu alpha. So this is basically giving you the flux of neutrinos for a given flavor nu alpha at a neutrino energy E nu. Then this flux multiplied by the neutrino energy and then summed over all neutrino flavors, the 3 neutrino flavors, divided by 3. So this is basically the average of the neutrino flux, the neutrino energy density coming from individual neutrino sources, neutrino flavors. That should be related to the corresponding flux of photons. And here I would have the photon flux that goes like K pi over 4. And here I have now E gamma squared Q gamma E gamma. In this quantity is, so the E gamma that I introduced here, that is the corresponding gamma ray energy from pions, neutral pions, which are produced by the same cosmic ray interaction. And from our earlier estimate of neutrino and photon energies from hadronic emission, I know that this neutrino, this photon has a gamma ray energy that is twice the energy of the neutrino. And this factor k pi, that is the ratio between charged pions compared to neutral pions. Yeah, so this always goes into the balance between gamma rays and neutrinos. I need to know how many pions are, what the relative contribution of charged and neutral pions are. And so, for example, in PP interactions, this factor k pi, as I said earlier, should be a factor 2. In P gamma interactions, this k pi factor is of the order of 1. So this quantity here is the neutrino emission on production. So this gives you the total power, the luminosity of neutrinos produced by cosmic ray interaction, and the corresponding power of hadronic gamma ray interaction. And the gamma rays which are produced by astrophysical sources, they are unfortunately not directly observed at Earth. So let me go back to this slide that I showed you earlier. So gamma rays can interact electromagnetically with cosmic radiation backgrounds, in particular the cosmic microwave background. And as they interact with the cosmic microwave background, they produce pairs of electrons and positrons. So if we calculate the interaction length of this interaction for the cosmic microwave background, we arrive at this red line. And you see that for PeV gamma rays, so 10 to the power 6 here, we have a very low interaction length, which is basically at a distance that is comparable to the distance of the galactic center. So high energy PeV gamma rays can actually not be observed from extragalactic sources because they will get absorbed by the cosmic microwave background via pair production. But these high energy electrons and positrons that you produce, they can, on the other hand, again, interact with the cosmic microwave background via inverse Compton scattering. So this leptonic process we talked about the day before yesterday. And this will produce, again, high energy gamma rays via this process. And these gamma rays can then, in the second round, interact again with the cosmic microwave background. So this repeated pair production and inverse Compton scattering is initiating electromagnetic cascades, which will eventually end up in the gamma ray range below about 1 tera electron volt. And this is the gamma ray range, which is actually observed by the Fermi satellite. So this is here an observation of the Fermi satellite looking for the diffuse isotropic emission of the universe. And this is at this level here. The black data points are observations made with IceCube. And if I now look for different models of PP, so cosmic ray gas interactions or cosmic ray interactions with radiation, I can calculate what should be the corresponding emission of gamma rays after we have taken into account electromagnetic cascades in the universe. And what one can observe is this very puzzling observation that with this very high neutrino flux that we observe, we would basically expect that we saturate the observation of the gamma ray background. So this is very interesting. It could mean that what Fermi sees in gamma rays is exactly coming from the same sources as we observe in IceCube. But this story is too good to be true. It turns out that the gamma ray background here on the left-hand side is actually dominated by blazars. So active galaxies with a jet pointing into our directions. And we already know from our comparison of diffuse versus point source fluxes that blazars cannot be the dominant sources of high energy neutrinos. So that means there's only less than 100% that we can actually squeeze into the gamma ray background, which is otherwise dominated by these sources. So this is at the moment a problem for models that try to explain this neutrino emission. What could be the answer, and this is going to be the last thing that I'm going to say, and then I have to stop. So what could be the answer is that this emission is actually dominated by sources that produce the neutrino flux via interactions with photons. What can happen in these sources is the following. If you have a very strong efficiency of cosmic ray interactions with these backgrounds, then automatically this requires a high background of target photons. And these target photons, on the other hand, are another source of pair production with high energy gamma rays from your hadronic interaction. And this pair production rate can be so high that if you have hadronic emission in the source, it actually is not able to escape from the source. It's basically converted internally in the source into other electromagnetic radiation bands. And this would be one way to accommodate the fact that we observe a high energy neutrino emission, but on the other hand, we have to find a way to reduce the corresponding gamma ray emission in the Fermi Lagrange. So I think I should stop now in the interest of weekend. The thing that I was not able to discuss with you is also very interesting relations between the neutrinos and ultra high energy cosmic rays. But if you are interested in the neutrino ultra high energy cosmic ray connection, you can maybe also ask me and Johan in the office hour that we are going to have in a few minutes. Okay, thank you very much for your attention on a Friday afternoon.
Thank you very much to you, Markus, for all the nice lectures.
Can I ask a question?
Please.
Yeah.
Could you go to please page 34?
This one, yeah.
Yeah. Yes. I don't know how to read this kind of figures. I just know, for example, for the white star, it's represent the characteristic of this source, right?
Mm-hmm. Exactly. Yeah.
But what's the meaning of the blue region and these lines? I don't know how to read them.
Okay, so the magenta line that you see here, this is a combination of possible sources parameterized in terms of their local density and luminosity that would allow to explain the isotropic flux. So the calculation that I made with you earlier was showing that the isotropic flux is proportional to the effective density that I called rho zero times the neutrino flux. And that is the reason why this line here appears at this angle. Yeah. So the product along this line, this is a logarithmic plot here. Along this line, you basically have a constant contribution like this here. Mm-hmm. The blue line, on the other hand, this shows you, so this line here, this is a combination that goes like the neutrino luminosity times density to the power 2/3. And this dependence, unfortunately, I did not have the time to walk. It's very elementary, but I only gave you the final result here. This was the outcome of the contribution of the closest source. Yeah, so you have a population of sources and they are randomly distributed in our universe to a first approximation. Mm-hmm. And one of these sources will appear statistically very close by. And you can estimate what is, statistically speaking, the contribution of this closest source.
Okay.
And you see that this source gives you luminosity times density to the power 2/3. And now we bring in this information. We have not observed very strong neutrino sources. So there's not like a Crab nebula, which is one of the standard candles in gamma ray astronomy. We haven't seen this. So this combination has to be smaller than our detection threshold. And so the position of this line here is basically set by our detection threshold in IceCube. Yeah, so the blue region is excluded by non-observation.
Okay.
Does this make this a bit clear?
Okay. So in this case, for the 20 times S cube, they have it have the potential to detect all these source, right?
Yeah, exactly. So this is actually one of the money plots that we show to funding agencies. If we approach them to ask them to build a larger detector, we tell them that if we had a detector with 5 or 20 times the capabilities of IceCube, sorry, I didn't mention that. So this is the current IceCube. This will be future IceCubes. Yeah. Then we would also cover here the range of very frequent sources that individually have a very low luminosity, like starburst galaxies, for example. Yeah.
Okay.